All right, this is week 11 for the Digital Fundamentals course. This will be the final lesson, complete lesson for this course. And the topic for this week is shift registers. So a shift register is an electronic circuit that allows data to be shifted from one location to another. They're used in various electronic applications. One example for this would be, let's say we have a calculator and you want to enter the number 328 on your calculator. And we don't have a key that is 328, but what we do have is we have a 3, we have a 2, and we have an 8. So if we want to enter that number, we would have to enter them by pressing those 3 keys individually. Now the process that we actually go through when we do this is a 3-step process. Basically, we're going to detect that we have a numeric entry, so we detect that key press. We're going to read in the value of that key, and then we're going to store that in memory. So basically, detect, read, and store. That is our 3-step process. So that's how we get our first number. Now if we want to press the next number, we can't just repeat that process again, because when we store, we're going to be storing into that same memory location. So we need to clear that 3 out of there first and put it somewhere else. So that is what we call a shift of our original data to a new memory location. So our process now is going to be detect, read, perform this shift, and then store. So we're going to detect that a number has been pressed. We're going to read what it is. We're going to shift our data from our memory storage location, for our first memory storage location, to our second memory storage location, and then we're going to store that new data in our incoming storage location. Okay? When we do the next one, it's the same thing. We're going to detect and read. This time we're going to do 2 shifts. We're going to shift over here. We're going to shift over here. And then we're going to store into this location. So this process that we're doing here, this shifting process, is basically what a shift register does. And register is another term for a memory location. So we are basically shifting the register each time we get a new number. So we're basically loading up all these data memory locations as we go. Now, there's 2 different methods of doing this. The first one we're going to talk about is serial, which is basically we move 1, then we move the next one. That is serial. Or we can do parallel, which is where we move things as chunks of data. Move or store as chunks of data at a time. That would be called parallel. Now to create a shift register, a D-type flip-flop works really well for this, to create a serial type shift register. They're good because they use one data line and a clock signal, in order to be able to store data. So this is an example here of using multiple flip-flops, D-type flip-flops, to create a shift register. So what we'll see here, we have our input here. This is our input signal. This goes to the D signal of the very first flip-flop. We're going to call this flip-flop 1. Call this flip-flop 2. Flip-flop 3. Flip-flop 4. Change colors here. You will also notice here we go from the Q of flip-flop 1, connect that one directly to the data entry of flip-flop 2. Q of here goes to the data entry of the next one. And we keep on repeating that process for as many flip-flops as we have. So remember, a flip-flop is basically a storage device. So we have either a 1 or a 0 in each of these. So let's say, for example, we have an input coming in here. That's going to be a 1. Let's say we already have a 0 stored in here. We have a 1 stored in this one. We have a 0 here and a 0 here. Let's look at how this flip-flop is going to function. So we have our input. We have our flip-flop 1, 2, 3. Currently, this is loaded up like this. So at the time when we get our clock signal, what happens when we get the clock signal? So we clock, and what happens is this is going to move into here. We are going to look to see if our Q, we'll go from this direction. If our Q was on here, it'll trigger the data input here. So this 0 basically moves over to here because if Q was on, we'd have a 1. If this was a 1, we'd have Q on, which would trigger the data here, which means a 1 would transfer across here. If Q is off, in this case where it's a 0, that means this is off. We have a 0 on the data. When this gets clocked, we get a that 0 over here. And this process basically repeats. So you can see this data basically transfers as we go. So basically that 0 goes over here. This 1 goes over here. This 0 goes over here. And this data in 1 goes over here. So let's say we now, for the rest of this duration, we're going to turn this input back to 0. Next time we clock it, this is going to travel over here. 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 And our new input is basically a 0. So what you're basically seeing is these 1s travel across. When they get to the end, when this one gets to the end, it basically has nowhere to go. It just basically falls off a cliff, and that disappears. Okay, so this is basically the action we see on the shift register, is these 1s basically traveling through the shift register until they get to the end, and then they disappear. So you'll notice as well, all of our clock signals are all tied together. So clock signal, clock signal, clock signal, all tied together. So this all shifts synchronously. Okay, so that is the serial shift register. So looking at the waveform here, we have our clock pulse. If our data signal is a 0, when we clock it, we get a 0 here. If our data signal is a 1 when we clock it, we get a 1 here. This next one is looking at what is the status of this one. So this was a 0 when we clock it, so we get a 0 here. This was still a 0 at the time when we clock it, so we get a 0 here. This was a 1 when we clocked it, so we get a 1 here now. This is now back to a 0. It's a 0. Now it's a 1. Okay, so you'll see that traveling through, and basically what you see is this is the same as this, except this one here, each flip-flop is basically the transformed version of the previous wave. Okay, so it's just moved a bit to the, it's moved one clock pulse to the right. Okay. We call that one clock pulse later in time. All right, so we can build the serial. This is part A of the lab. We can build this serial shift register. We have a signal here that is connected to the clear of each one, so that gives us our ability to clear. So I can empty out everything. And then we have one switch here, which connects to the data of the very first flip-flop. And then everything is just Q connects to data, Q connects to data, Q connects to data. Okay, and then all the clocks are all tied together. Clocks are all tied together. And then what we should see is when we put a 1 over here, you'll see a 1 travel basically across here like that. Okay, so on your board it will look like this. And we will watch the video from the Darren Holmes. So you'll see as he flips the data switch to on, so he's removing clear, turning the data switch on. You'll see the 1 travel from flip-flop 1 to 2 to 3 to 4. So that's the data input. So traveling across there. The blinking light on the left was the clock input. And you should be able to see this. We populate this table as part of the electronic submission. Okay, so that is the serial load shift register. And we can perform this one in TinkerCad as well, which we will do now. Alright, so this is the TinkerCad version of the serial load shift register. So I have gone and put in twice as many flip-flops and LEDs as the one calls for in the lab, just because I find with the 4 it goes through really fast. You don't really get to see what's going on. Putting 8 in here, it's basically the same circuit, just repeated again. But you get a better chance to see them actually, see the ones actually traveling through. So let's look at what we're doing here. So we've got some switches. This switch here is going to represent our data. So when this is in the down position, the data is on. When it's up, it's off. This 4th switch represents the clear. We turn it up to clear. We have a 1 kilohertz or a 1 second clock pulse coming in. And we're powering at 6 volts on our power supply. So our clock is the yellow wires. So you'll see that goes to the clock of all 8 flip-flops that I have. So clock, 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 clock. That connects. All these orange wires are all the clock signals. I've got the clear is going to the reset on each of these. So there's 2 resets on each chip. And then I basically have this yellow wire goes to the input on the very first one. And then we go output to input, output to input, and we just keep repeating that process. Input goes to output, output goes to input, and that process just repeats, all cascades all the way through. And then we also connect up the outputs to our LEDs as well. Okay, so let's watch this thing run. So if I put in some data, you'll see that starts to load up as long as I'm holding the data down. I shut it off, we start to put in zeros, and you'll just see those shift across the shift register as it goes. So I put in just one single, you can do that. It's basically, is your switch on when the clock pulse hits? So let's try to put 2. I'm going to try to put in a pattern of 3. Let's do a 2 and then a 1. A 2, and then off, then a 1, off. Oh, I missed it. And then whenever this is running, anytime I hit the asynchronous clear, it shuts everything off. Okay, so that is the serial load shift register. So this is kind of fun to play with. It makes a nice little pattern of lights. You can build this with yourself out of only 4 LEDs and 2 chips, so that's 4 flip-flops altogether. So this is part A of the lab, and this should be the one that you submit on. You can submit this one for your TinkerCad submission for this week. Okay, so this was the serial load shift register, part A of the lab. Okay, we're going to move on from the TinkerCad demonstration. Now we're going to talk about the parallel shift register. So parallel uses a JK flip-flop instead of a D-type. Parallel lets us load data into multiple memory locations all at once. So we can load up a specific pattern and then run that because we can load individual flip-flops all at once. So this is how we wire it. So what you'll notice here, so first of all, like the serial, the clocks are all tied together. So clock, clock, clock. These are all tied together, so they are all being triggered synchronously. Now this is probably where the similarities end. Let's start looking at the differences. So we have Q here. So if we have a 1 in here, we want to transfer that 1 over to here. So that means we want to do a set on this one. So Q is going to connect to the J of the next flip-flop, and we will repeat that pattern. So Q connects to J of the next flip-flop. Then when we get to the end here, you will notice what we're doing on this one. We are coming all the way back here, and the Q here connects to the J of the first one. So what this is going to create is basically a wraparound. So we will go from here to here to here to here. When we get to here, instead of falling off the end like they have in the serial flip-flop we just made, this will come back around to here again. So these will basically just run around in a continuous loop. Okay? So that was doing the set function by connecting the J and the Q. So let's say we have a 0 in here. A 0 will mean that the Q bar is on. Now what we're going to do here is connect Q bar to the K, because that will trigger a reset and make this 0 transfer over here. And then we're going to go Q bar goes to K, Q bar goes to K, and Q bar on this last one wraps all the way around, comes back to K on the first one. So that is how we connect the flip-flops together. You'll notice that the clears all connect together and go to a switch over here on our dip switches. Now, how do we actually get data into these? This is where we use these other switches here. So the preset of each is connected to an individual switch. Okay, so each one is connected separately, has its preset connected separately to an individual switch. So what we would do here, if we wanted to set up a pattern, so this allows us to load separately each individual flip-flop. Find my cursor here. So if you wanted to set up a pattern of 1, 1, 0, 0, what you would do is you would set this switch and this switch. That would trigger the preset here and preset here. And you would make this one off and this one off. So that would put in a 1 and a 1 here, and a 0 and a 0 here. If you set those up as presets and then set them back to the regular states again and then started clocking it, then this pattern would loop around in a circle. Okay? So we're going to watch that demonstrated here. So there's some interesting things that are done in this video here. So we'll watch this go. So you can see that pattern of 2 lights. Now he just cleared the whole thing. Now he's removing the clear. Now he's going to set some data. Now what you're going to see him do over here, if you watch this, what he's doing, he's pulling out the resistor that's part of the clock. Now by doing that, what happens is you'll see that the clock signal has now stopped because he pulled the resistor out. So one thing you don't want to do, you don't want to have this thing trying to run as you're setting the data. So he pulled out so he basically stopped the clock. He was able to hit these 2 switches here, which set the data on here. And now he puts the resistor back in. The clock starts going again. And now he's got that pattern that he set running through. So it's running this way. He just cleared it. So he's doing a clear again. Now he's going to set this one. Looks like. Turns that down. That runs through. So that is the parallel loads. You can see how he was able to set 2 inputs on at the same time and then start that up when he started the clock again. Okay, so that is how the parallel load shift register works. Now, unfortunately, we are not able to create this one in TinkerCad because the JK flip-flop that we have in our TinkerCad is not the same as the one that you have on your breadboard, because our JK flip-flop in TinkerCad doesn't have the preset function. So it has the clear but not the preset, and because of this, we don't have a method of getting the data into the flip-flops to start them off. So we can create everything else, we can make the loop, but we don't have a way to actually get data into the flip-flops to do the parallel load of them. So I tried to do a couple workarounds for this, but I couldn't get anything that worked well. So we are not able to demonstrate this one in TinkerCad, unfortunately. Alright, so moving on, we've got some TTL shift registers. So the one in the book and in the lab is the 194. So what you'll see here, it has the ability to shift right or shift left. It has separate inputs for that. So you can trigger it to either shift to the left or do a shift to the right. Everything else is pretty much the same. You have a clear, you have a way to load it, you have outputs, you have a clock pulse to it. So it wires up like this, and then you can demonstrate how you're able to set a pattern and then have it run to the right. You can see this one is looping around, so it runs to the right and then comes back again. And now what he's going to do is he's going to change the configuration of the switches. He's actually going to make it run back to the left. So you'll see, I think it only does one cycle here, but he makes this light go to the left on the next one. He does one pulse to the left and then he stops. Then the video stops, so sorry. But you can see how you were able to change direction on that one. So that is that shift register. Now we can't do that exact one, but we can do a similar TTL shift register in TinkerCad, so I will demonstrate that now. Alright, so this is a TTL shift register. This is the 595 chip, which is described as an 8-bit shift register. So this has 8 pins for output. It's got 2 clock pins. It's got a clear, and it has an input. And then our power, and it's got an output enable, which we need to have powered, or need to have that turned to ground. Actually be a black wire. But it wires up like this. Okay, so I've got 2 signals here. I've got one that's a data signal and one that's a clear. And this basically operates in the end. It looks a lot like the what we did for the serial load shift register, but it's basically 8 flip-flops contained within this one chip. So it wires a lot easier than the serial load, but it performs exactly the same. So we turn this switch to enter data. We start seeing ones come across. We can shut that off. See those ones travel. This does not wrap around. We can basically put whatever pattern we want in there. We can turn this switch to clear it all out. And it just continues to run like that. So this is the 8-bit shift register chip. This is the HC595. So this is our best TTL shift register chip that we have in TinkerCad. So give this one a try as well. It should operate pretty much the same as the serial load setup we did before, but it's a whole lot simpler because it's all integrated in one chip. We're not making it from individual flip-flops. Okay, so this is our version of part C of the lab. All right, so why do we need to know how to use shift registers? What's the importance of these? So this is actually something you will see down the road, especially when we start doing some PLC logic. This is a common method of part tracking in industrial applications. So when you do PLC Part 1, we use a software called Logix Pro, or at least we're using it right now. I don't know if we'll still be using it when you come through, but there is one application in there that actually uses some bit shift commands. So this is a common way to do part tracking within a system. So what you'll see here, this is, I'll get some different colors here. This is the simulation for a bottling line. So here's what our challenges are with this line. We have different types of bottles coming down this line. They travel in this direction, which you'll see in a second. So we have one sensor here, which detects whether the bottles are broken or not. We have another sensor here, which detects if the bottles are tall or short. You'll see there's two different heights. You'll see these ones with the red cracks in them, those are broken. And we have another sensor here that detects whether they are present or not. So the way our bit shifting logic for this works, present this is basically equal to our clock pulse. So every time we read a bottle, we use that as our clock, and that basically triggers our bit shift. Okay? So we're going to set up a bunch of registers here, and we are going to track ones and zeros. Basically, each spot here represents one spot on this line, or one bottle, basically. Okay? So first thing we do is we track whether bottles are tall or short. So this is basically our 0 point, or right here. This is our next point, right here. This is our next point. This is our next point. This is our next point. So this tall is going to be equal to a 1 at that point here. So the way this pattern would load up here, if this was our bit shifting, all of our data that gets recorded here, every time we see a tall bottle, we write a 1 into this register, and then every time a new bottle comes along, we shift all that data to the right. So basically, if you look at all this array of bottles here, it would represent as talls and shorts. So for the talls, it is going to look something like this. So we have, at this point, we have tall, short, tall, tall, short, tall, tall, short, 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 tall, short, tall, 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 short, tall, tall, short, short, short. And we don't really care past that. Okay? For the brokens, we're going to start here. We're going to do a similar thing. We're going to put a 1 every time we get a broken. So we look good, 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 good. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The 10th one. 1, 2, 3, 4, 5, 6, 7, 8, 9. That's a broken. 1, 2, 3, 4, 5, 6, 7. And then all the rest are. So in our logic, the reason this is important, we have a couple of operations here we need to watch. So when do we need to know whether we have a tall or a short? So the first thing we need to do is this here is our our filling operation. So we fill differently depending on whether we have a large or a small bottle. So we do the large fill on a tall, we do the small fill on a short. We don't do any fill if it's a broken. So we need to look at this. So the capping operation from the perspective of tall is 0, 1, 2, 3, 4, 5, 6, 7. The seventh spot in our register. So 1, 2, 3, 4, 5, 6, 7. This spot right here, this number here, if that is a 1 in that register, we have a tall bottle at the capping station. If it's a 0 in the register, we have a short bottle in the capping station. And we will act accordingly. Same thing with our broken. 1, 2, 3, 4, 5, 6. It's the sixth one. 1, 2, 3, 4, 5, 6. This spot here, if we have a 0, that means it's a good bottle, we cap it. If we have a 1, it's a broken bottle, we don't cap it. Sorry, we don't fill it. Okay? Same thing with, there's two other operations that we look at here. Sorry, a couple other operations you'll see going on. First of all, we have our reject chute right here. Broken bottles fall down here. We have a capping operation here. We track to see if we have a good bottle here. As long as it's not broken, we cap it. And then there's another decision we make over here depending on what mode we're running in. Sometimes we run broken bottles down here. Sometimes we separate them into tall and short and put the short ones down here or the tall ones down here or something like that. But basically, we load up our shift registers based on these 3 switches, and then we make all of our decisions down the line based on the rest of this. So let's watch a little video of this thing in operation. And remember, we are populating these 2 registers with 1s and 0s based on every time a new bottle comes in, which is our clock signal, and then putting in a 1 or a 0 based on the status of these 2 switches. So this is like our data onto our flip-flops, except this is all being done through a PLC instruction. So let's watch this run. So this goes quite fast, but you can see the proper color liquid going in there, whether it's the tall, whether it's the large, or the small fill. I'll probably slow this down a bit here so it runs slower, and you'll see only the presence of good bottles are being capped. You'll see there goes a bad one down the reject chute to be ground up and put into a box. You'll see the capper is only firing. So this guy is only firing here. So it won't go here. It will go when there's actually a bottle there. So the only way it knows that is by following that shift register. Here's a tall. Next one should be a short being filled. Next one will be a short being filled again. So you can see that small fill running. We'll have another small fill running. Next one will be a large fill running, large fill, and then it goes super fast. Now I switched modes. I think this is mode B down here. Now we're putting the broken bottles down here instead, so this chute opens up and drops the brokens down there. This is all being done through PLC logic, but it's a bit shift left, I think, or bit shift right PLC command that is essentially the same fundamentals as what we were doing with these shift registers. So it needs a data signal, it needs a clock signal, and then that's basically the way that it operates. Smashing some bottles here because it's going too fast. You can see those ones, the broken ones not being capped. Broken one won't cap. Okay, so lots going on in this one. It's pretty cool to watch. But that is a good application of part tracking using a bit shift. Okay, so that is how we can use a bit shift for something practical in the automation world. All right, so that is it. We will see you on Thursday to answer any questions you have about this. That is our last lesson for this course. We will just be doing review from here on out, leading into our final test. Okay, so good luck. We'll see you on Thursday.